Hello, I'm Kang. I am from Hanyang University and I am doing a visiting scholar at Stanford. Today I will present the transcranial ultrasound technique using dual mode conversion by wedge transducer. Transcranial ultrasound stimulation (TUS) has great potential in neuroscience and clinical research because the TUS has higher focality and deeper penetration depth with the non-invasive condition. Most TUS techniques used focused ultrasound with a single or array of transducer by normal incidence. There are two big limitations. One is the high attenuation in the skull that can make a high acoustic loss, and the second one is heating problem in the skull when we use high intensity ultrasound. To overcome these problems, we propose the wedge transducer technology for dual mode conversion. This is concept of this technology. From longitudinal waves in the wedge to a high order land waves in the skull, then from the land waves in the skull to longitudinal waves in the brain. High transmission efficiency of the dual mode conversion approach can reduce acoustic loss and heating the skull. The wedge angle is given by Snell's law, determined by the ratio of the speed of sound in the wedge to the speed of the selected land mode phase velocity. This is a theoretical land wave dispersion curves of the skull when the skull thickness is 6.5 mm. We chose the A2 mode considering the wedge design and the marginal behavior compared to the neighboring modes at 500 kHz. From the phase velocity, the critical angle was calculated by 23 degrees. To verify this concept, we carried out some simulations with the FEM software. Left one is normal incident transmission and right one is wedge transmission. The important factor of this simulation is the attenuation in the skull. So we assume that the skull is viscoelastic material. We chose the viscose damping and we need the bulk and shear viscosity. We already have a reference attenuation coefficient of skull. Based on the relationship between attenuation coefficient and viscosity, we could calculate the viscosity values. We compared both by using pulse integral intensity for checking the transmission efficiency. And result shows that the 20% high transmission efficiency in wedge transmission. And also in 2017, our group conducted some experiments with the aluminum and skull fragment by conversion transducer. And we also got the result that shows the wedge incidence has better transmission efficiency. This is the wedge transducer design using PCT element. The wedge angle is 52 degrees determined by the sum of calculated critical angle and the average skull angle. This is design of wedge housing and the skull model. Our plan is to evaporate the metal layer and insert the PCT element and connect with silver paste. Before making the full-size wedge transducer, we made a prototype, 1/8 size model. We made the wedge house by 3D printer with resin. And then we inserted 49 PCT elements into a 7x7 array of wedge house with the same pulling direction. We fill the gap by low viscosity epoxy and makes chrome gold coating by metal evaporation. And we made PDMS mold and cast the PDMS. Then we got the prototype wedge transducer after curing the PDMS. We conducted experiments with and without the skull. We scanned the pressure field by hydropon. The skull fragment has 6 to 7.5 mm thickness. We compared the beam profile and calculated the transmission loss by measuring the pressure. Without the skull, the maximum RMS pressure is 88 kPa. With the skull, the maximum RMS pressure is 13 kPa. And the total transmission loss including reflection is 16 dB. So we propose the dual mode conversion technique for enhancing transcranial ultrasound delivery into the brain using a wedge array method. This makes high transmission efficiency compared to the normal incidence. The next step is a comparison of the efficiency of wedge incidence for various land wave modes using the skull and making a full wedge transducer. Thank you for your attention.